Welcome back to Computer Science Theory. This is Comms W3261, Lecture 2, Part 3, Reducing NFAs to DFAs. So what we're going to do today is we're going to show that any NFA can be converted into a DFA that is equivalent, meaning it recognizes the same language. So we'll prove a theorem that implies this fact. This is the main takeaway fact. A language is regular if and only if it is recognized by some NFA. And why this fact is going to follow? Well, if it's regular, then it has a DFA by definition, right? That's the definition of regular languages, languages that are recognized by some DFA. And of course, a DFA is almost exactly an NFA. State diagram of a DFA is the same as the state diagram of an NFA. The formal definition of a DFA is almost the same as the formal definition of an NFA, except technically we're mapping to a set of states instead of a power set. Basically, it's a subset. So this direction is pretty easy. And then the bit that we're going to prove right now is going to be to show if you have an NFA, you can turn it into a DFA, which of course means the language is regular. So that's what we're going to do. Theorem. Every NFA has an equivalent DFA. And before I prove this theorem, I want to talk a little bit about what our strategy is going to be. Good place to start, usually before you start a proof, you should have some idea of where you're going with it and what the core insight of the proof is that'll make it work. All good proofs have about one idea in them. Well, it's not always true, but sometimes if you've got more than one idea, it might help to break it into more than one proof. So what do we do when we're executing an NFA that makes it different from a DFA? The only difference is the transition function, and the key is this set of states idea. At any point in the execution of a DFA, we have exactly one state that we occupy. But at any point in the execution of an NFA, we might be occupying, well, 0 states if the computation is died, 1 or more states, each containing a different branch of the computation. So a momentary snapshot of an NFA is going to be some subset of all of the possible states, the states that we occupy. And we're going to take that, turn that snapshot into a state in our DFA. That's our strategy. So our DFA will use every possible set of states in the NFA as a single state in the DFA. Our transition function will then simulate the actions of the NFA, right? I want to make a DFA that does exactly the same thing as our NFA. So how's it going to work? Well, we're going to have states that capture NFA states, and we're going to make sure we move between them in a way that tracks how the NFA works. And the proof is just going to be a construction. It's going to take exactly this form. So proof. Let n equals q sigma delta q0 and f be an NFA that recognizes the language A. We'll build a DFA, and we'll call this DFA M Q prime sigma delta prime Q0 prime F prime. So all of these symbols are slightly different except for sigma because we're using the same alphabet. That also recognizes A. And the proof is just defining what this n is. So in particular, our set of states will be the power state of Q. And that just accords with our strategy, right? We'll have a state in our DFA for every possible set of states in the NFA. Our alphabet is the same. We'll get back to Q0 actually. What should our ending state be? Well, what we want, when do we want our DFA to say yes? We want it to say yes when the NFA says yes. The NFA says yes if, once it reads all the symbols, at least one branch of the computation is in an accept state. So we'll define our set of accept states to be all states in Q prime, such that this set of states contains an accept state of n, right? And then finally, we want to define our transition function, and I guess our start state. We want to define delta prime to act like our NFA does. So at each step of our NFA, what happens? Well, we start in a set of states. We read in an input symbol, S, and we go to all states reachable from R by S edges. And then 3, we go to all states reachable by epsilon arrows or epsilon edges. That's what happens when we run our NFA. So we want our transition function in our DFA to mimic this process exactly. So to do this, I'm going to define something really quick. For every subset of Q, we'll let E of R denote all states reachable from R by epsilon arrows. That'll make it easier to write this last bit, step 3, without using a lot of English. So now we can define delta prime as follows. Well, we're going to start in a set of states R, and we're going to take in an input symbol S. All right? And then we'll go to a set of states. That set of states will be all states in Q. So we're going to a set of states. Remember, in our DFA, this is a single state. identified by this set. All states in Q, such that Q is in the set of states reachable by epsilon arrows from all states that you can get to by transitioning on A edges, sorry, I don't know where I got A, by transitioning on S edges, that's our input symbol, for some R in R. Right? What's going on here? Well, I'm taking in a set of states R and an input symbol S. I'm then considering all of the places I can reach from R by S edges and all the places I can reach from there by epsilon edges. And that determines my next state in my DFA. And now finally, I'm also going to define Q0 prime to be the set of all states you can reach by epsilon edges from the start state, the state containing Q0. So that's our complete construction. And why will this work? Because we're going to simulate the NFA at every step. We start at the start state. We consider all the places we can get to using epsilon arrows from there. We'll embody the state where our DFA will start. And then at every single step, we look at our DFA state. It corresponds to a set of NFA states. That takes us to a new set of NFA states, which corresponds to one new state in our DFA. We accept precisely once we finish reading all the characters of the string, if we're in some state, which corresponds to an NFA state with some accepting branch. So this is maybe one of the highest level kind of meta proofs that we've done so far. So it's all right if it's a bit of a head scratcher. It'll help to understand it if you sit down and you think about, okay, what is our DFA doing on every single input? How is it evolving? To see that a little better, I'm going to do an example of the procedure we just laid out. In particular, I'm going to draw an NFA state diagram, and then I'm going to draw the DFA corresponding to it that acts on the set of states. Okay, let's do this example of converting an NFA to a DFA. And we'll do it on the example alphabet AB, because we've been leaning on 0, 1 a little heavily. So here's a little NFA. Just drawing some edges so we've got all three rules in play. All right, that's our NFA. And now what we want to do is define a DFA, which is a 5-tuple, Q prime, sigma, delta prime, Q0 prime, F prime, using exactly the rules that we outlined in the last proof. So 1, Q prime is just power set of Q. That is, it's the set of all subsets of states in Q. So we'll have state for the null set. We'll have a state for the set containing 1. We'll have a state for the set containing 2. A state for the set containing 3. We'll have a state for 1, 3. A state for 1, 2. We'll have a state for 1, 2, 3, and what have I forgotten? Oh yeah, 2, 3. So 8 states. This is the entire power set, all subsets of Q. So our DFA is going to be quite a bit bigger. Our start state, Q0 prime, is just the set of all states reachable by epsilon arrows from Q0. So in particular, our start state in our NFA is 1, and we can reach 3 using an epsilon arrow. So the start state in our DFA is 1, 3. Our set of accept states is going to be the set of states in Q prime such that R contains an accept state of our original NFA n. The only accept state of our original NFA n is 1, so the set of accept states in our DFA is going to be all the states that contain 1. So that's 1, 1, 2, 1, 2, 3, and of course 1, 3. The tricky bit, and forewarn you, if I make a mistake here, just, well, you can't let me know. You're on YouTube. If you're in the classroom, let me know. So our transition from a set of states given a certain input symbol is just going to be a set of all states Q and Q, such that Q is reachable using an epsilon arrow from some state that's reachable on the input symbol for any R in R. Right? And we'll do a few of these as an example, and then I'll finish it up and leave the rest as an exercise. So we'll start with maybe the most puzzling one, which is this null state at the top. Null state means we have no live branches of computation. So if I read in any symbol in our alphabet, either A or B, my branches go nowhere. I stay in the null state. But this changes if I'm actually occupying some state. If I'm occupying state 1, for example, and only state 1, and I read in an A, what happens? Well, there's nowhere I can go, so that branch of computation dies. In other words, we go back to the null state. That is, after we read in the A, we're occupying no states in our NFA. On a B, however, I go to state 2. From state 2, if I read in an A, I both stay in state 2 and move to state 3. This whole time so far, there's been no epsilon arrows I can take. So stay in state 2 and move to state 3. So we go over on an A to state 2, 3. And on a B, we just go over directly to state 3. From state 3, on an A, I go to state 1, but then I can take my epsilon edge. Remember that we're going to the set of all states reachable by epsilon edges after I've done my transition, my first transition edge. So from state 3 on an A, I go to 1, and then I also go back to 3. So I end up in state 1, 3. On a B, computation dies. I'll do the last state I'm going to walk through will be the state 1, 2, 3. And then I'm just going to fill in the rest. So you can pause and do this last bit as an exercise and then check with me if you like. So on 1, 2, 3, when I read in an A, what happens here? Well, from 1, I do nothing. There's no A edges. From 2, I stay in 2, and I proceed to 3. From 3, I take the edge to 1, and then of course I take the epsilon edge back, but that doesn't matter. And at the end of doing that, I have a state, a live branch in every single state. So I go from 1, 2, 3 to 1, 2, 3 on an A. On a B, I go from 1 to 2, from 2 to 3, but from 3, I don't go anywhere. So there's no way to get back to 1. I go from 1, 2, 3 to 2, 3. Now I'm just going to fill in the rest. And pause for a moment. This is what the completed DFA looks like. It's clearly a lot more complicated because it's a generic construction. So we do see that although our NFAs are no more powerful than our DFAs in the sense that any language recognized by an NFA is recognized by a DFA, the DFA sure might use a lot more states and edges. So our NFA might be cleaner. We can actually clean this DFA up a little bit by observing that the state 1 and the state 1, 2 both don't have any incoming edges. So if we wanted to, we could just erase them. That is, we know there's no path from the start state to these states. So removing them will not change the function of our final automaton. So that's our NFA to DFA example. Next lecture, we'll see how to use NFAs to prove regular languages are closed under regular operations. So this is an extension essentially of what we did when we proved the regular languages are closed under union. If A and B are regular, A union B is regular. You can prove that a lot quicker with NFAs, and you can prove other things with NFAs as well. So we'll rapidly expand the techniques we know to prove that a language is regular. The reading that corresponds to this whole lecture, all of lecture 2, is SIPSR, end of section 1.1 and section 1.2. And as a reminder, homework 1 is due Tuesday, 7/6/21 at 11:59 p.m. via Gradescope. Thanks so much for watching. Have a great day.